If you replaced our Sun with the largest star currently known to science, its surface would immediately swallow Mercury, Venus, Earth, and Mars. The physical edge of this expanding star would continue pushing out into the cold reaches of the solar system, finally stopping just short of Jupiter's orbit. To understand how massive that is, consider that our own Sun is already large enough to fit 1.3 million Earths inside of it. Stars do not start out this massive. An object can only reach this kind of scale when the standard rules of physics begin to fail. For most of a star's life, it operates under a strict compromise. The immense mass of the star creates a crushing inward gravitational pull, which is countered by the outward pressure of nuclear fusion burning in the core. As long as those two forces remain perfectly equal, the star holds a stable shape for billions of years. Finding the physical limit of how large a star can grow requires looking at exactly what happens when that balance breaks. It is tempting to think that the heaviest stars in the universe naturally grow into the largest ones, but mass and volume do not perfectly align in space. A healthy star sits in a stable state called hydrostatic equilibrium. That stability ends when the star runs out of its primary fuel. Without the outward pressure of that specific fusion reaction, gravity takes over and forcefully crushes the core inward. This intense compression superheats the core, igniting secondary fuels like helium. This new reaction burns far hotter than the original, creating a violent outward explosion of pressure that drastically inflates the star's outer layers. This process creates what astronomers call a red supergiant. The record-breaking size of these bodies is a symptom of a star actively losing its internal battle with gravity. For years, researchers have tried to pinpoint exactly which of these dying stars is the largest, with famous contenders like WOHG64 and UY Scuti holding the title at different times. Calculating their true size is difficult. They are located thousands of light years away, often hidden by thick clouds of galactic dust that require highly specialized observatories to peer through. But the bigger issue is the anatomy of the stars themselves. They do not have a hard, solid surface like a rocky planet. Instead, astronomers measure the photosphere, the diffuse, blurry region of gas where photons finally escape the star's density and travel out into space. Because a hypergiant's edge is essentially a thick, shifting fog of gas, pinning down its exact limit will always carry a margin of error. Even factoring in those uncertainties, the current leading candidate stands out. Hidden deep within a massive star cluster lies Stephenson 2.18. Current estimates place its radius at more than 2,100 times that of our Sun. At that scale, you could fit roughly 10 billion of our suns inside its total volume. If you were to travel around its equator at the speed of light, a single lap would take you nearly 9 hours. It is so massive that it forces astronomers to question the theoretical physical limits of how large an object can grow before it tears itself apart entirely. Despite its intimidating scale, Stephenson 2.18 is incredibly fragile. It is barely holding its shape. Because its outer layers have expanded so far from the core, the gravitational pull keeping them attached is remarkably weak. This results in an extreme stellar wind. The star is constantly bleeding its own mass out into the vacuum of space. Becoming a hypergiant is a violent, temporary phase defined by a star shedding its mass. Eventually, this phase will end in a core collapse supernova, destroying the star completely and scattering heavy elements across the galaxy. By comparison, our Sun seems incredibly small, but that modest size provides the exact gravitational balance required to burn steadily for billions of years, giving life on Earth the time it needed to take hold.